We're going to take a look today at a situation in which we are given pictorially the graph of f of x, and we're asked to sketch a graph of g of x, which involves certain transformations of the given graph f of x. And typically in a situation like this, we would look at the equation for g of x and identify parts of it as whatever their respective transformations are, and then attempt to shift the f graph about. We're going to go at that backwards this time, and we're going to look at, could I attempt to graph g, and in so attempting to graph g, identify what those transformations are. So let's start, as with any good graph, by making a table. Now I know you typically say you can't make a table for g of x because g of x depends on this f function, and when there comes the point where I need to evaluate the f function, I don't have the algebraic representation of the f function. However, we do have a graph, so we can evaluate f. If the stuff inside here turns out to be a specific number, say 1, we could look on the graph and say, well, when x is 1, f of x is 4. And we'd be able to evaluate it graphically, and then use that 4 to continue calculating what the output would be for g of x. Now I want to stop for a moment before we approach this and just ask the question, what would it look like if nothing was happening inside here? What would happen to this graph if there was nothing going on inside? So in that case, the g of x function would simply be the opposite of 1/4 f of x plus 4. So if you were to build a table for something like that, you'd look at what are my inputs, and we're putting values in to the g function and getting them out. However, in this case, when you put a value into the g function, it immediately goes into the f function. So we have the opposite of 1/4 of whatever f of, and that input becomes an input in the f function, which we could immediately evaluate. F of 0 graphically is 4. And we could continue to find the output for g of 0. It'd be 1/4 of, this number is now 4, plus 4. And we could calculate that. 1/4 times 4 would be 1. And then add those two together, you get 5, and the opposite would be -5. So there's our output. And we could continue to do that. You could go back, and instead of the 0, we could put in, and it would probably be wise of us to pick values that we can evaluate with f. I wouldn't put in a 10 because I don't know what the f function is at 10. But I might put in, say, a -2 to my g function, which then becomes a -2 going into the f function. Well, f of -2 we can see is still 4. So this work carries on much the same. 1/4 times 4 would be 1. 1 and 4. We would also, when we put in a -2, get a -5 in the context of graphing g. Now, more importantly, look at what that's actually doing to the values. When you plug in a value for g, out comes the 4, but what happens to it? A series of things happen to the y value. It gets reduced to 1/4 of what it once was. Then it gets increased by 4 up to 5. And then it gets negated, comes out at -5. So our input values for this simplified version of g, once you've evaluated the f function, whatever value you are at on f, that value simply gets made to be 1/4 of what it was, which is your vertical compression. It then gets increased by 4, shifts it up 4, and then we would have a reflection. So we could come up with a pretty good sketch of this just by plotting those points and by looking at how the rest of that should work. So we've already said we have a couple points for this new function. When we put in a 0, we got out of -5. Put in a -2, we got out of -5. And if we picture this whole operation here getting compressed vertically, gets squashed down to be 1/4 of what it was. So we have, let's see, this is 5 1/4 maybe, so 1/4, that's just a little bit higher here. This used to be way up at 4, it's now down at 1. You'd have, I don't know, a rough sketch, something like this. And then it got shifted up, so all of that's happening 4 units higher than it used to. So instead of hitting at 0, we hit 4. These that were at 1 are now up at 5. It's a little higher. This one's up 4 here. So you'd have, and this is again just a rough sketch, something going on like this. And the whole thing got flipped over the x-axis. So that point there is now down here at -4 and -5. This was a little above 5, is going to be a little below 5. And everything is then going to be happening the opposite of what it used to be doing. So something like that. Now that of course only explains what's happening outside the parentheses. But if we start with the easy stuff, so if we start by what happened outside the parentheses, it gives us a leg up when we get to the tough stuff. So as we're working through the tough stuff, we'll note, okay, we've got out of the function, now we're just going to do whatever happens vertically. Now let's attempt to actually graph g of x. So we're going to build a table, same way we did before, by putting in x values. But this time, we have an additional challenge. Because when you put a value in for x, it goes through a series of changes based on our formula for g of x before you actually get to evaluate the function. For example, if we were to put in a -8 for x into this function here, it would look like this. And then inside here, we have a couple things going on. Before we can do anything in terms of evaluating f, we've got to take that -8, cut it in half, change its sign, and decrease it by 2. So g of -8 would be we'd get a +4 here, cut it in half and change its sign. And when we get to this point, we need to know what is f of 2 if we're going to be able to keep going. But when we look at our graph, we can't evaluate f of 2. f of 2 is out of the viewing range here. So when we put in a -8, it's not that there isn't an output, but we miss it. We can't see that point on the graph. Now we know which point we're interested in. We're interested in the point 2 something on the f graph. We don't know what that is. But this particular input choice wasn't a good one. We'll say we missed. Not that it doesn't exist. But more importantly, let's make a note. What is the corresponding value of, or ordered pair in f of x we were interested in? We didn't know the output when the input was 2. -8 as an input for x became 2 as an input for f, and we didn't know what the output was. So let's try a different value and see if we can get one that'll work. Let's jump down to -4, let's say. So as we put a -4 into this function instead of a -8, calculations are going to be very similar. -4 times -1/2 is a +2. 2 minus 2 comes out to be 0. So g of -4 does turn out to be something that we can evaluate. Because we know how much f of 0 is graphically. F of 0 is 4. That's the place in this computation where we move across from having an f to not having an f in our calculation. We've now evaluated f of 0. It came out to be 4. And we can continue this process to get an output for g. 4 times 4 is going to be 1. And we've been here before. Increase it by 4 and then change the sign. We get an output of -5. So we now have our first point that is truly on the graph of g of x. The other version wasn't actually g of x. That was just a simplified version of g of x. But this really is g of x. -4 for an input gives us 5 for an output. Let's plot that on here. -5. Now more importantly, look at the point where we went across. F of 0 equaling 4 is what allowed us to calculate this. So that means this corresponds to that point 0, 4 on the f function. If you look at that place kind of in between the cusp and this local maximum here, that point there, that's what this is on the g function, because that's the place at which we came across through the f function that we evaluated f. And we could keep going. We could plug in another value. Let's try 0. If we put a 0 in to g, we have -1/2 times 0, which is nothing. Take away 2, -2. Again, we're plugging the 0 in. And then f of -2 is a point that we can evaluate. When I plug in -2, I get out a 4, according to my f function. And these calculations are much the same. 4 times 4 is 1, adds up. Once again, we get -5. And we'll start to see this thing take shape. So here's our second point. When we plugged in a 0, we got -5. To what does that correspond? That corresponds to the point at which we evaluated f. We plugged in a -2 and got a 4 in the f function. So this corresponds to the point -2, 4 in the f function. So here are these points that match up. When I look at 0, 4, and -2, 4, so it's these 2 points right here, 0, 4, and -2, 4, those became, and it ended up switching them, these 2 points here. And I'm noticing that it looks like this thing got stretched out horizontally. Those 2 points used to be closer together, now they're further apart. It also changed their orientation. Recall that when I put in a 0, that's when I came out over here. So we've seen some sort of a stretch and some sort of a flip, and our question is, why is that happening? What's going on as we plug values in? And I think it's going to become more apparent if we look at the actual operations here. So let's start to evaluate this while considering what the actual x values are doing. If we, for example, wanted to continue our table and we wanted another value for x, let's say we wanted to do a 2. Think about what actually happens to the 2 when you plug it in this function. We may or may not be able to come up with an output, but think about what's happening to the 2 when it goes into this function before you can evaluate. The first thing that happens is you get half of the 2. Then you change the sign, which is how we would get to -1. Once we're there, we reduce it by 2. So that'll take us down to -3. Can I evaluate f of -3? Hey, we can. Look at that. F of -3 appears to be 7. So once you've evaluated, then we have an output. -3 came out to be 7, so that's our point that this corresponds to, that -3, 7 there. And then a 4th times 7, we get 7/4. We add 4 to that, so this is about 1 3/4, and we're about 5 3/4. So -5.75. So that gives us the output. We're at -5.75. And it gives us the ordered pair at which we crossed over. -3 came out to be 7. And we can plot that, but let's look at where it went first. We plugged in for g a 2 right here. And when we plugged in the 2, half of it was the first thing that happened. Then that, and this is what we're doing with the x value on the x-axis here. 2, with half of it was 1. The opposite of that put us over here at -1. And then we decreased it by 2 to get to here. So now we're going to actually ask the question, what would happen if I was to try to figure out where does this point go? What kind of transformation would get me from the f point, -3, 7, to the g point that we just discovered? And recall that that g value was when we put it at 2, we got -5 3/4. Right about here. In order to trace it backwards, we have to realize something significant about all of these operations inside the function. They are not doing things to the x value of f. They are doing things to the x value of g. When you put in a 2 for g, it takes half of it, and then it reflects it, and then it reduces it by 2, or shifts it left 2. So if you want to know, how do I get back, you of course can figure that out as long as you know how you got there. When we have a g input, The G input has a series of things done to it. First, we take half of it, then we negate it, and finally we subtract 2. And the result is an F input. So we use the variable x in both situations, but the x's are inputs into G in the beginning, a bunch of stuff happens to it, then that x input is an F input. So let's say we want to go backwards. I know I ended up with an x input of, in this case, this point right here is -3, 7. The input for F was -3. What G value would correlate to that? Work backwards. I would have to add 2. So that'd take me to -1. Then I would have to negate it, which would put me at +1. And finally, I would have to double it in that order, which would take me to 2, to find, that's our G input. The G input of 2 corresponds to a F input of -3. So what happened to this point, -3, 7? Well, in terms of the horizontal component, if you think about the x value, look at our sequence, you added 2 to it, you negated it, which brought it over here to -1, and then you doubled it, which pushed it out to 2. Because those are the opposite operations in the opposite order of what G is actually doing. This stuff inside tells you what G does to an x value. All these operations are what G does to an x value to get to an F input. So if you want to start with that point, you've got to undo them, and it's very similar to solving. In fact, we could have taken an algebraic approach to this. We could have said, I know that I'm going to have -1/2 times my number minus 2, and I want to come out with that -3. I want to get to the F input of -3 here. How would you have figured out what x is? Same story. You would add 2 to both sides, and then you could multiply both sides by -1, and then to undo the half, you would double both sides. So the same steps that you do to solve algebraically, in the same way that you start with what's furthest from the variable by the order of operations, and undo those in order until you get all the way to the variable, that's the same order that we undo this stuff. We're now ready to graph this using transformations. So let's start with that point that we just had, -2, -3, 7. So if I take -3, 7 here, I'm going to first adjust it horizontally. I need to add 2 to it, then I need to negate it, which puts it over here, and then finally the x value gets doubled. So now I'm out here at 2. Once I've done that, then I come through the f function. And the f function puts me out here at 7. Now we're doing all of the things that we did previously outside the function. So we're using that -1, that 1/4 and the +4 and the negative there. So you would then say, this point gets, just as we practiced before, 1/4 as tall